Hello all of you. Welcome to the 29th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about heat equations. We first derived the heat equation in general form, then we have simplified it for one dimension for the case of a slab, and then we did some examples on the slab problem with different boundary condition. In this lecture, we will extend that idea to some other examples, first in heat equations, but then also in diffusion equation for mass transfer. So, let me begin with the problems now, but before that I want to emphasize that until so far we have been working in Cartesian coordinates, just because the geometry we are dealing with, the slab was rectangular, right, and Cartesian coordinates were more convenient. But in general, we can work in any coordinate system. The only difference that we will have is the definition of the del operator and accordingly the del square operator, right. So, let us say when I work in the cylindrical coordinate, then instead of x, y, z, the variables are going to be r, theta and z, and we will have unit vectors in r direction, theta direction, z direction, and there is going to be slight change in the derivative forms coming there. In the spherical coordinates, we will have r, theta and phi, essentially two angles, and again there will be some change in the derivative forms, and you can look up this in the tables, but I have put it here. And accordingly, in the del square also there are going to be some changes in the del and del square operators. So, whenever we need that, we can look up here and use the corresponding expression, whatever is important. Because in general cases, let us say you have a cylindrical rod, then the Cartesian coordinates are no longer the best choice. You prefer to work in a cylindrical coordinate, and if you have a sphere, then you prefer to work in the spherical coordinate. So, we will take examples and then we will do that as appropriate. So, let us take this first example. So, you have a cylindrical rod of certain total length L and some diameter d, which I can also say twice of its radius r, that is being heated in a convection heater using the arrangement shown in the figure, right. And what you see here is only the portion of this rod is immersed inside the heater, and that portion corresponds to a length of h, and the other portion, the L minus h, is exposed to the ambient. That is what is said here. So, a portion of length h is being exposed to hot air inside the heater at a bulk temperature Th, and other portion of length L minus h is exposed to ambient air at temperature Ta outside the heater. So, here some temperature is Th, here the temperature is some Ta. Now, the question says to develop a model to determine the temperature distribution inside the rod, and then explain without solving how the temperature distribution inside the rod will change as a function of the model parameters, and to justify your answer. So, let us try to first question ourselves that how will we simplify the heat equation in this case, right. So, let me first write the general form of heat equation. Before that, let me draw the geometry again just for my own convenience. This is my h, this is my L minus h, there is some radius r or diameter twice of r, some ambient temperature Ta here, some ambient temperature Th here. Now, you can imagine that it is preferred to use the cylindrical coordinate as opposed to Cartesian coordinate. Is there some symmetry here, right? And the answer is yes, there is some symmetry here. If you draw the axis of the cylinder, there is no change in theta direction, right. If I take, for example, any point for a given value of r, if I look at the theta even inside the cylinder, there is no change, there is no variation with theta, because the heating is same in all the directions in the theta direction. Of course, heating is changing below a certain height and above a certain height, but that's in the z direction. In theta direction, there is no change, right? So theta direction is if I rotate anywhere on the top or inside the heater, there is no change in that, right? So we can clearly ignore the theta terms, right? So we can again use whatever we have used for the center line symmetry argument and say that my dou t by dou theta is not important. So I can ignore that or ignore, right? So I will not say 0, I can simply say it's ignored because there is no theta variation. So no theta variation. And if I also see that as a result of that, if I see a temperature at, let us say, some R value and some minus R value, right, they have to be the same, because T at R and T at minus R for a given Z, that is going to be the same, right. So we can simply say that T of R for a given Z is equal to T of R at minus R at Z, and that pretty much gives me that dou T by dou R is equal to 0 at R equal to 0. That is what is known as the radial symmetry. So because of radial symmetry, we have no theta variation. So all the derivatives of theta we will not consider, and I will set dou t by dou R equal to 0. Just like dou t by dou Z equal to 0 in the slab case, we can say dou t by dou R equal to 0 in this case, right. So this boundary condition is sorted out. So now we do not have to consider theta variations, and we have got one boundary condition already for the R direction that applies everywhere. It applies here also, everywhere along the axis of the rod. I can apply this particular condition. But still the question is that should I ignore any of the derivatives? So now I am left with the derivatives dou t by dou Z and dou t by dou R. If, for example, this rod was not divided like this, if the entire rod was inside the heater, then our choice would have been easier. We could have said that my radius is much less than the length of the rod, and therefore we can have taken only dou t by dou R by the same argument which I have done earlier, because the R is now the smallest, the dimension compared to Z, right, because my radius is much less than the length of the rod. So I could have only considered the R variation, right, but I cannot do that here, because clearly we know that there is a variation in Z direction. In fact, there is a discontinuity, because beyond a certain value of Z, we are exposed to the ambient condition. If I do not consider the Z variations, there is no way we can account for that, right. So we need to consider both Z and R derivatives, right. So we cannot make this choice of one dimensional heat equation. We do not need to also, right. If there is a no choice, if the one dimensional approximation is not good, we can go for the two dimensional or three dimensional approximation, right. So let me go back and look at the expression of del square from here. So now I will drop the second term, because theta variations I have ignored, but I still have the first term and the third term in the heat equation, right. So I am going to write my heat equation, which is rho Cp dou t by dou t is equal to k del square t is equal to k into 1 by R dou by dou R, R dou t by dou R plus dou 2t by dou Z square. So this becomes my partial differential equation. And now we can ask ourselves how many initial and boundary conditions do we need. So, we still need one condition for time because we have first order in time, right, but we can define it for inside heater and outside heater. But the question gives you some initial temperature, it does not seem to give an initial temperature. So, we can assume that the temperature everywhere is uniform to begin with, right. So, we can say that my initial condition is at t equal to 0, my t is some t naught. But now the boundary conditions, if we think about it, we have second order in t and we have second order in z. So, in fact, we need 4 boundary conditions, 2 for r and 2 for z, right. Let me first look at the boundary conditions. So, we have already figured out one boundary condition, dou t by dou r at r equal to 0 is equal to 0. But what will happen at r is equal to capital R, the surface? Can we equate the conductive flux to the convective flux? The answer is yes, but then that equation will be different inside the heater and outside the heater, because the ambient temperature is different for inside and outside, right. So, the BC2, I can again equate my conductive and convective flux minus k dou t by dou r at r is equal to capital R. But now this will have two equations, one inside the heater, and that is going to be, I will define a coordinate system, z equal to 0 to h is inside and h to l minus h to l is outside. So, this will be equal to something like h into t minus th for z less than h or less than equal to h, and this will be equal to h t minus ta for z greater than h. Now, in principle, the heat transfer coefficients inside and outside can also be different. So, let me call this some h1 and some h2. Now, let me do the same thing for the z. So, where do we define the boundary condition for the z? So, now again, if it was completely immersed inside, then there will be only two boundary conditions for z, z equal to 0 and z equal to L. But now there is a problem because there is a intermediate boundary as well, right. Well, let me first do it for z equal to 0. Now, we are looking at the conductive flux coming here and the convective flux going out, right. And again, I can equate something like minus k dou t by dou z at z equal to 0. And now, since I have defined my z direction as positive in this direction, it will make sense to put a plus sign here to account for that, right. And this will be equal to something like H1 inside the heater T minus TH, right. At Z equal to L, I will have something similarly, but now the flux is going in the opposite direction. So, I have something like minus K dou T by dou Z at Z equal to L. This will be equal to H2 T minus TA, because ambient temperature is TA here and TH here. And then what can we do at this boundary Z equal to H, right. So, what should happen here, right. So, what definitely should happen here is the temperatures must be continuous as we cross the boundary, because I mean, like, what is the reason for a discontinuity, right? So there is a heating. Of course, the temperature will eventually change from here to there if you think about like this, but at the particular surface, we can assume that the temperature is continuous. It's continuously changing because the property of the medium is no material is not changing. The outside media is changing, but the material properties are not changing really. So we can, I mean, we can have a logic to say that the temperature inside is continuous, and so is the flux, right? So we can imagine that the temperature and the flux minus kT by kdt by dz is continuous at z equal to h. Now we can go ahead and we can define it in dimensionless terms, and we will have now basically two Biot numbers coming from here. The first number will be something like h1 into h by k, and second will be something like h2 into L minus h by k. And in fact, k can also be different in the two medium if the k is temperature dependent, but we can imagine it's the same rod, so thermal conductivity remain constant. So we'll have two Biot numbers. And now for T cap, now earlier we have defined something like T minus Ta by T naught minus Ta, but now we have two ambients, one is Ta and one is Th, right? So we have to pick one of them. In fact, we can solve it separately for the bottom part and inside the heater and the part outside it, but that will probably make it more complicated. So I can probably make a choice of one of them as the ambient. Let's keep Ta as the ambient, and I can define Z cap still as Z by L, and I can probably also define the T cap in the same way, but keeping in mind that the final equations are going to be much complicated than what we had. And in fact, it is no longer a one-dimensional heat equation, it's a two-dimensional heat equation, right? And so we can imagine that the variable separable form that was only in terms of theta, t and z will not be sufficient. We will have a third function, and most likely the boundary conditions are not going to remain homogeneous, right? So we need to probably go for numerical solution for this problem, but at least this is the way we can start framing this problem. Right? Now the question also asks you to guess what is going to happen, right? And it's not very difficult to say what exactly is going to happen. Let me first plot how the temperature is going to vary with Z. From 0 to H, it is inside the heater, so temperature must be high. And from H to L, it is outside the heater, the temperature must be small. And there are two limits that we are having set by the ambient conditions, right? So Th is the temperature of the ambient in the heater, and Ta is the ambient outside the heater. They show the behavior at like very long times. If it eventually reaches the steady state, then we should have something like this. Until Z equal to H, it is inside the heater. So it should be like this, and then goes to this. That gives me a real discontinuity, right? But in reality, the situation will not happen. We will have some smooth transition, although drastic, from there. So this is the behavior at T going to infinity, but in reality, it will not be obtained. And in the beginning, you may be anywhere, but let's imagine that you start from some T naught somewhere here. Then the temperature inside the heater will start to rise, and temperature outside will start to become lesser because T naught is higher than Ta. So inside we have heating, outside we have cooling. So temperature profiles may start looking like this for some time, then eventually something like that, and finally something like this. And how exactly it changes depends on the magnitude of H. If more part is inside the heater, then clearly the temperature profile will be more towards TH than towards TA. If less part is in the heater, then it is more towards TA, less towards TH. And of course, it depends on the conductivity and heat transfer coefficients and things like that, right? So we can see it's still the heat equation, it's two-dimensional heat equation. The equation is clearly more complicated, and we cannot hope that it will be easy to solve by the variable separable method. But nonetheless, forming the equation and setting up the boundary conditions is something that we can still do based on the ideas. And once we have the set of equations, we can figure out maybe how we can numerically solve this equation. Okay, so let us look at the next problem, and it is probably something that is closer to what you have seen in Indian homes, right? So the problem says that roti or fulka is made on a hot flat plate tawa, you must have seen this, getting desired heat from an LPG stove underneath. A cylindrical duff of radius r and thickness d is placed at time t equal to 0. Let me, just because I will define one other variable here, let me call that thickness as h, just to avoid that variable, and we'll come to see what variable I will talk about. At time t equal to Tf, it is flipped, so that the other side also gets, face also gets heated. Further, at time t equal to Td1, the roti is placed on a direct flame without the hot plate in between, again flipped at direct flame, and finally removed at time t equal to tau. Making reasonable assumptions and listing them, develop a model to determine the temperature and moisture content of roti, that is something new that has come up, as a function of time, starting from the duff at t equal to 0 to the final product at t equal to tau. Now, there are two phenomena happening here. First, there is a heat transfer from the tawa to the roti, but as a result, the duff that is initially wet is becoming more solid like, because the moisture inside the duff, the water inside the duff is getting evaporated, and that is what is giving me the basically the crispiness or in the roti, and the fact that the roti basically have this kind of effect where the inside you have like a vapor forming, right. So we want to discuss both these effects in a single problem, right. So let me look at the first effect, the temperature, and the second effect, the moisture, separately. But in order to do that, we have to make some assumption right here, right. So the assumption goes like this. In reality, I begin with a duff, and this contains the moisture, right. So this already has the moisture, and eventually it forms the roti that does not have the moisture. What happens to the moisture when we provide heat? So, providing heat here, when we provide heat, the moisture gets evaporated, right. So, basically water will form like bubbles and then escape the thing, right. So, we get an extra latent heat from the evaporation of the vapor, right, and that escapes outside. So, we can imagine that whatever effect that is having is not inside the duff, but it can be a boundary condition, right. So, when we derived our heat equation, we assume that the conduction is only the medium of heat transfer. We did not consider this phase change and all the effects, right. So, one way is to see that how this bubbles are affecting the heat transfer inside the duff, that will change the governing equation, or to simply say that there is an extra heat coming off because of evaporation, and that gives me an additional flux at the top surface that we can account for separately. Only then we can write the heat equation for this problem in the same form that we have written, right. So, the point I am trying to make is my equation that I have derived, that is derived not considering any phase change. In order to use that, we need to ensure that the phase change effect is handled somewhere separately, in this case as some kind of a boundary condition, right? Rho Cp dot T pi dot T, right? That's the first assumption we make. The second assumption we make is whatever moisture is there, that is more or less is coming out by diffusion and going out, right? So, in that case we can use the Fick's law, dou C, the concentration of water, dou T by D, dou 2 Cw by dou Z square, or in general I can write D del square Cw, where C is the concentration of moisture. And if I say that some Cw naught is my initial concentration, I can also talk in terms of moisture content as something like Xw as Cw by Cw naught, that is how much percent of moisture is left, and provided that Cw at naught is some constant and uniform across the duff, we can also write this equation as dou Xw by dou T as D del square Xw. Okay. So, provided we can write the equations as such, that means the phase change effect is not considered in this equation, and the moisture is handled by the diffusion equation. The diffusion is the governing mechanism here. In there also you can have convection effects and all that, but just to have a starting point, let us assume that the moisture diffusion is the dominant phenomena there. Then in that case we have two sets of governing equation, one for the temperature and one for the moisture. Now let us look at the typical Roorkee geometry and try to see like what kind of one dimensional assumption that we can make, right. So, if you see from top, it looks like a circle, and from the side it looks like something like this, right. So, there are 3 dimensions here. The cylindrical coordinate is more relevant in this problem, but what is happening here is my z direction, the thickness is much less than the radius of the Roorkee, or it's, I mean, anyway we are assuming that it is circular. So, the radius will be same everywhere. If it is some other shape, then there can be other dimensions, right. But let us say the radius. So, if r is much bigger than h, then provided that we have taken our coordinate system as this is z and this is, we can ignore the variations. And in fact, we can also ignore the theta variations, because the same logic what I applied in the last problem, in the theta direction there is no change, right. So, you can ignore the theta variations. So, now in the z direction I have two equations, one for the temperature, the other for the moisture. For temperature we have and for moisture we have okay. Let me now set up the initial conditions. So, for initial condition for temperature clearly is something like T is equal to some T naught, and for moisture we can say Xw is something like 1, right. The Xw is the ratio of the concentration of moisture with respect to initial moisture content. So, it is 1 to begin with, right. And now we need the boundary conditions, right. What is the boundary condition at z equal to 0? So, at z equal to 0 we have some heat flux Q, right. So, the boundary condition there at z equal to 0, we have some heat flux q. Keep in mind that there is no center line symmetry now in z direction. The bottom surface is in contact with the tawa and top surface is with the ambient, right. So, at z equal to 0, we have something like the conductive flux is given by my q, and for moisture, the moisture cannot go into the tawa, right. So, clearly my dou x w by dou z is equal to 0. So, we have initial condition for both the governing equation. We have the first boundary condition at z equal to 0 for both the equations, and then finally, the second boundary condition at z equal to h. Again, we can equate the fluxes, right, for the temperature. So, this gives me something like minus k dou t by dou z at z equal to h is equal to h T minus the ambient temperature, right. And then for the moisture, there are many ways to deal about it. We can set the diffusive flux equal to convective flux outside, but the convection will anyway be much bigger than diffusion, right. So, it does not harm to say that at z equal to h, my x w will be something like whatever is the moisture content in the ambient. We can in principle consider the variation outside, but assuming that the convection outside is much bigger than the diffusion inside, we can have something like this. So, we have set up the initial conditions, the boundary conditions for this problem, and now we can do the case of flipping and all that. I will not write the equations, but what is going to change is when I am flipping it, the initial condition is what will we have at the top surface before flipping. So, first I have to solve from 0 to Tf, and then whatever temperature I achieve at the top surface, that will become the bottom surface temperature from Tf onwards, right. And when it is going on the direct flame, then instead of that Q, that is the effective heat flux coming from the tawa, now I have to look at the effective heat flux coming from the stove. So, clearly even in this case, whatever I have done, this Q, whatever I have put here, is the heat flux from the tawa, right. So, how do we get it? Eventually it should depend on the heat flux from the stove, and we need to account for the conductivity of the tawa, right. So, this is clearly less than the direct heat flux if it is on direct heat, right. So, all these things has to be done. There are additional equations in this particular case for the tawa that I have not written, and for direct flame that additional equation will not appear. But then you can imagine there are other effects because now it is in direct contact with the flames and things like that, right. But what I have given you is some kind of starting thoughts of how we can model this kind of a problem, and then again it is flipped and things like that. We can start thinking of this kind of problems which are coupled problems of heat transfer and mass transfer, beginning with the idea of heat equations and set up with some assumptions the boundary conditions and all that for these kind of problems. So, let me very quickly do some other problems, right. What is given here is Arvind is a chemical engineer working in a major cosmetic firm, and the firm is interested in developing a gel formulation that prevents the skin from sunburn during high daytime temperature. He calls you from help in developing a simple numerically solvable model for the temperature distribution in a gel layer of thickness Hg applied on skin of thickness Hs much bigger than Hg, and then based on the knowledge, the heat equation knowledge, whatever I have given you, try to help him do a model. And then it is also said that the body is not providing any additional heat to the skin, and gel and skin has different thermal properties, right. What we can do here, so we have now two layers, a gel and a skin, and we want to prevent sunburn. That is my final objective. If the gel is not there, then the temperature of the skin will rise too much and may become red. So, the gel is trying to prevent that, right. And essentially how much gel is able to prevent that depends on how much is the penetration of this temperature inside the skin, right. So, skin, deep down the skin, the temperature is same as the body temperature, that is my ambient temperature for the body, that is around 37 degrees Celsius, right. And let us say the outside temperature is some 50 degrees Celsius. So, the gel should ensure that there is not much temperature difference inside the skin. It doesn't, temperature doesn't penetrate so much inside the skin, right. So, I want to basically form the model from that perspective, right. So, again I can write the heat equation. So, I can write it, I can define Z equal to 0 at the skin surface and Z equal to Hg as the gel thickness, and the skin thickness can be pretty high, Hs, but we do not want the temperature to penetrate, temperature effect to penetrate so much deep down, right. So, we pretty much want to seize the heat flux into deep down the skin, right. So, let me define some depth of penetration d such that for Z equal to minus d, my dou t by dou z becomes 0. I do not want the temperature to change below this value, right. So, somehow this, how much d we can obtain, what is the minimum value of d we can obtain, that basically gives you my efficiency of the gel material that I am having, right. And now we can write the again the heat equations, and again you can imagine that one of the directions is important here, the Z direction. Other direction, the skin, the face of the skin is much bigger than the thickness of gel. So, we can write the heat equation, but now we can write the heat equation both for the gel and for the skin, and we have something like, for the gel, the properties are clearly different, and for the skin right. And I have to set up the boundary conditions, right. So, there are two different PDEs. So, both requires their own initial condition and boundary condition. For the first PDE, we can set the boundary conditions at the top surface, right. Again we can equate the conductive flux and the convective flux there, right. That is one possibility. The other possibility is we can set the surface temperature to be equal to the outside temperature. I think the first one probably is better. So, we have at Z equal to Hg, we can say minus k g dou t by dou z is the heat transfer coefficient T minus the ambient temperature. And then at Z equal to 0, again we have to equate the heat fluxes, but now coming from the skin to the gel and into the gel. So, basically we have to equate two conductive heat fluxes, that will be minus kg dou t by dou z is equal to minus ks dou t by dou z, z equal to 0 by the way. So, I am talking about this surface between the gel and the skin. So, the conductive flux into the gel is equal to the conductive flux coming out of the skin, right. And so, we have got the two boundary conditions. The initial condition we can again set at t equal to 0 this is equal to some T naught of the gel material or Tg naught. And for the second equation, for the skin, we already said that we want to have certain depth of penetration at which the flux has to go to 0, right. So, at z equal to minus d, we want to set dou t by dou z equal to 0, that is my first BC. And the second BC, I can equate the fluxes again, but I have already used up this condition. Keep in mind the temperature of gel and temperature of skin is coupled together. What else I can do? The temperature still I can assume is continuous. So, I can assume that temperature of the gel at z equal to 0 is temperature of the skin at z equal to 0. This will ensure I am not repeating the same condition, right. So, if I have 2 PDEs, I need 6 conditions, right. So, I cannot use the same condition in both the PDEs, right. And again, I have an initial condition at T equal to 0, my T is whatever is the body temperature, right, provided that I go outside after applying the gel formulation. So, earlier my body was already at the body temperature, right. So, I can formulate therefore problems, different kinds of problems based on this idea of heat equation, and we need to be very careful in setting up the boundary conditions, the initial condition, but what we also need to ensure that it is consistent. We have as many conditions as we need to solve that equation, and that should be like the first requirement in whatever you do, right. I am going to end very quickly on the last problem. I will not completely solve it, but just to give you an idea. So, this is a mass transfer problem. So, we have a solid spherical capsule of a certain radius r, and this has some initial concentration of drug molecules in a polymer matrix. And at time t equal to 0, the capsule is placed in a large water beaker of size much bigger than the capsule size, and the concentration of drug molecules at a distance r from capsule is given by the Fick's law, and I can develop the analytical model of drug concentration, right. And then what will change if the capsule is swelling and things like that, right. So, let me quickly tell you without solving in detail what is going to happen in this case, right. So, we have spherical coordinate and theta variation is negligible. So, we already have dropped it, right. And the other phi variation, there are two angles in spherical coordinates, azimuthal and polar angle. So, variation in both of them are neglected, right, because there is symmetry, spherical symmetry in this problem. So, only the r direction is important, right. And we have something like this for the concentration, right, and the capsule is placed in a beaker. The beaker is very big. At r equal to 0, again we can use spherical symmetry. And I can say that my dou c by dou r is equal to 0, and at r equal to r, we use the fact that the beaker is very big compared to the capsule. Capsule is very small. So, the volume of the beaker is very big. If the drug comes out and goes outside, then it is going to a much bigger volume, and concentration therefore effectively is 0 by simple mole balance, right. So, let us say for example, the volume of capsule is some Vc, then whatever concentration we have in the capsule into Vc is the concentration in the beaker into volume of beaker, right. So, the concentration in the beaker is something like Cc Vc by Vb, provided everything goes out. Then also the Vc by Vb is very small because the beaker volume is much bigger than the volume of the capsule, right. So, we can easily assume that the concentration is outside. It is known in literature as the perfect sink conditions, right. So, outside we assume that it is a perfect sink. So we get C is equal to 0, and we have the initial condition that my C is equal to C naught at T equal to 0 inside the capsule. And now we can pretty much solve this equation. You can notice that it is already homogeneous set of boundary conditions. So we can get a solution very easily for this problem in the series form. And if you do that, I will not complete this problem. What you will get is something like this. The dimensionless concentration, I can define C prime as something like C by C naught, that is going to be in terms of dimensionless R, that is R by R, and I can define this T cap as something like T by R square by D, because R is my radius of capsule and D is the diffusion coefficient of the drug. So this is going to be something like Cn right, where I already have used up the boundary conditions, and you can see that it satisfies the boundary conditions, right, because if I put R equal to 0 here, this R cap becomes equal to 0, and then I can take a limit sin x by x, it becomes equal to 1, right, and then we can have the initial condition that tells me that n equal to 1 to infinity Cn that is equal to 1, right. So you can try solving it and try to get this particular equation, but the point remains that we are using this variable separable form, and essentially it's same heat equation in a slightly different form in a spherical coordinates. Instead of the temperature variable, now we have the concentration variable, and we can still solve it, and we can get the answer for this problem, right. So with that, I want to conclude this lecture. In the next lecture, I will take a somewhat more complicated practical problem, where I will apply this idea of heat equation combined with mass transfer, and see like how we can actually apply this idea of heat equation in the real processes, right. So with that, I want to conclude here. Thank you so much.